Should I start?
Just introduce you.
Okay, go ahead.
So this is Professor Chen from Johns Hopkins University and Beijing University.
This work was carried out with my colleagues in the State Key Laboratory of Turbulence and Component Systems at the Peking University, and also my students at Johns Hopkins University. I first would like to put this talk in perspective. I really enjoy this morning's introductory lectures about the wall-bounded turbulence and transition. But the question I'm asking here is how can one directly use fundamental physics they obtained, learn from our research on turbulence for modeling and simulation? They talk a lot of structures, a lot of statistics, and so on and so forth. How can we do that? I think a very important thing like conservation of energy and helicity in the infinite Reynolds number limit, and the constant energy flux in inertial range or scale flux, and even intermittent exponents, and the Reynolds stress structures. This morning we talk about. So what I try to say, in fact we can do this kind of thing through so-called constraint variation principle, such as the decimation theory, renormalization perturbation theory. In fact, I'm proposing here maybe we can do in the physical space the decimation theory. That's what I'm trying to do. In fact, we have done some even with intermittent correction exponents. In this year's physical fluids, the first issue, I published a paper. Maybe some may not know that. We constrain, in fact, the energy flux. We have constrained helicity flux. We also constrain the partial scalar. We also try the intermittent exponents. One example I can give it to you for the people doing large eddy simulation, they know that if you use a dissipative model, essentially you will not get a correlation very well. If you use the similarity model, you will not get that dissipation well. So in fact, you can do this type of constraints. For example, energy flux. You can correct both of them. So what I'm going to talk today is about another example. How you can use this constraint idea, learning from physics, try to do this so-called the multi-scale simulation. Nowadays people talking about detached eddy simulation and the RANS and the AOES coupling. So the problem here is that we all know that for large eddy simulation, resolution is a challenge. For example, we know that near the wall, your resolution in the demand increase very fast as the Reynolds number power 1.8, whereas outside, in fact, it's very slow. Okay, it's relatively slow. Therefore, people propose to do the RANS, in fact, near the wall region and outside to do larger eddy simulation. They need a couple. That's the essential idea. As nowadays, they're talking about using like a hybrid RANS and AOES. In fact, for this kind of simulation, also there's a problem. We may be able to use this constraint idea to overcome it. The two main methods is this branding method. So you compare RANS, AOES, eddy viscosity with different model, and then you brand them, use specific ad hoc function. A lot of people have done this. And also another model is so-called detached eddy simulation. Essentially solve one equation, but in different regions you use different coefficients and so on and so forth. But that's what essentially in the SA model, and I just said. To make a long story short, let me tell you, in fact, there are problems for all these approaches. The major problem, if you look at this, the essential channel flow for detached eddy simulation, mean velocity profile, you look at with different resolution, you always see that, in fact, you cannot really exact catch the log law. This morning, most people believe log law. Maybe there's power law as well. Maybe it's the correct one. Instead, you push the log law to some region here. You can see that there's some, there's 1 over k, essentially correct in pushed out. What is the problem with this? The problem is the following. The large eddy simulation RANS are based on opposite philosophy. The matching is problematic. Why is that the case? In the inner layer, essentially you're solving RANS model, which is diffusive, where outside is essentially advection dominated. So essentially, lack of small scales, fluctuation in the RANS area is the main shortcoming for hybrid RANS and AOES match. So you don't have small scale. Outside you have small scale. You need to allow small scale developed, then match outside. That's why you push your profile log layer push outside. That's all the problem. That's I believe, okay? And how we overcome this? Okay, there's a possible solution for this. There's a group of them. There's one approach by our colleague from University of Maryland, Pierre-Marie Hugo, put forcing term in the interface, generating the fluctuation. So essentially, you don't need a certain transition layer immediately generated. Of course, forcing has also problematic because you don't know the statistic and so on and so forth. So because you have to use white noise and so on and so forth. So here is our approach. Oh, yeah, that is essentially overcome the problem pretty well for some cases. Here's our approach. So we promote ideas, say, why not we constrain the Reynolds stress? So what we propose so-called Reynolds-stress-constrained large eddy simulation, called RSCAOES. What we are doing, we are going to solve the whole domain with large eddy simulation. But we try to constrain. So for this region, you are not doing free AOES. What I'm going to say, we develop methods. So AOES method or any model, you can constrain particular physical underlying physics. So what do we say? In this case, we constrain Reynolds stress. You constrain Reynolds stress for AOES in the inner layer. You can see the advantage. Why is that? Because the whole range of fluctuation, but at the same time, you have a split of a detached eddy simulation. What's detached eddy simulation? Detached eddy simulation tell you your inner layer, your Reynolds stress is their solution. I certify that. So the bottom line, can you do that? How you do this? That's the idea, okay? Let me tell you. Here's the idea. So essentially, you can write down the AOES equation. Then you can do the perform ensemble average. Then you essentially can see that this is a Reynolds equation. So these two equations you make a comparison, you got exact solution of this. The Reynolds, the stress, and this one is known. It's the Reynolds stress for AOES. Then this is subgrid stress, the average ensemble average. You got that exactly. This is exact relation. Now what do you do on this? You just decompose your model equation to mean a fluctuation, the real tau ij, the stress. But therefore, essentially, the mean is known. Suppose this is a known quantity. Suppose I given Reynolds stress, for example, given K epsilon model, algebraic model, SA model. Suppose I give you a model. Suppose you learn from experiment. Suppose you learn from physics. Now you know this physical quantity, then the mean quantity is known. We have developed a larger simulation. As long as the mean is known, we can do the larger simulation.
But you need ensemble average.
Say again?
Ensemble average in your calculation. Do you need it?
That's for all AOES, you need to do that anyhow. Right? You either do Lagrange averaging time, or you do space averaging. We have done both of them. Okay, time and space. So that's the essential idea. We have tried algebraic model, K epsilon model, and SA model. Let me. So for the fluctuation part, you can just go back to do the normal larger simulation to dynamic Cheminsky model and determine them. For interface, we can use the same as a detached eddy simulation, or you can use the interface to separate inner and outer layer is located at the beginning point of log layer, such as the Reynolds stress achieving its maximum. We've done this. So let me show you some our simulation results. That's the idea. I hope this idea is clear. Idea is a constraint, your Reynolds stress, put it back to your AOES simulation. Now let's see this. This is exact compare with DNS with our RSCAOES with the coefficient here they're based on different Reynolds numbers, and people know that. The adjustment between 5.5 to 5.0, we compare them for different Reynolds number. This essentially is a DNS comparison. It's inertially quite well. Now let's compare with the detached eddy simulation. There's several curves here. Detached eddy simulation is this curve, and AOES just normal AOES without constraint. This is 6.4 by 6.4 by 6.4 simulation. The DNS has done by 256 by 520 by 520. It's each direction 4 times reduce the size. You can see that. Turn out the constraint AOES matched to the log layer is quite well. For this particular Reynolds number, you can try again with 1,000. You see again match quite well, and try 2,000 1500 and try 2000. That's the highest we can do using small computer. I hope I can compare to our colleagues' higher Reynolds number simulation to compare with this. But turn out it's quite well. The reason, as I said, you don't have this push-out effect. You got both good part. So the philosophy I'm promoting here essentially, when you do this kind of modeling, we have a Genoma equality. People know that through LES. This is a fundamental geometrical symmetry argument. But my personal feeling, more than that, you have to add back to so-called physical underlying physical constraints, which may help you to overcome these kind of problems. So that's what's my philosophy here. Let's see. Okay, let's calculate the drag coefficients. This is a comparison of drag coefficients. And compare our model without a constraint dynamic Sherminsky model and DES with different Reynolds number. You can see that this is a calculation for up to 2000. The coefficients, drag coefficients, compared with the Dean's, the friction law, we make a comparison. It seems like this model is not bad at all compared with others. Also, let's look at, so the comparison, the DES interface, our interface are not really changing too much. We just assume there's a maximum of stress. We also compare other Reynolds stress quantities with most DNS, compare very well with yours. And also we compare velocity fluctuation with different directions. Turn out this quantity, this is the results for DES. Of course, they cannot catch it, but our results compare quite well with the traditional dynamic Sherminsky model for this part. But our mean velocity is much better in this case. Also, you look at stream fluctuation. People already published that. This is DES. You don't see small scale. You see a lot of larger scale in the inner layer, which in fact is not correct. We compare. This is the results. This is the result from dynamic Sherminsky model and our constraint model. They are all consistent. We are working on try to adapt this kind of model for complex geometries. And here is our conclusion. I leave some time for discussion. RSC LES use the same grid resolution as DES. The inner layer flow solved by RSE LES possess sufficient small scale fluctuations. The transition of the mean velocity profile obtained by this method from inner layer to outer layer is quite smooth. This method is a simple method and may improve DES and the forcing scheme. And we have tried to time average and so on and so forth. It turned out to work quite well. So my conclusion is, when we do this kind of large eddy simulation or numerical modeling, I hope that we can use this morning's talk, fundamental physics, directly put into your model. That's my hope. Thank you.
Thank you very much. We have lots of time.
When you were constraining your Reynolds stress in the near wall region, are you constraining the whole tensor or just the shear stress?
We as a whole
Whole tensor.
Whole tensor. We can either use the K-epsilon model or we can algebra model. Even we can match the solved. Then we use this to constrain the large eddy simulation. We can solve it simultaneously, solve the equation.
But you're
SA model.
constraining U squared and D squared as well as the shear stress.
We use RIG, fully constrained.
Whole R.
Yeah.
So when you were doing that, like when you were comparing the channel or any other one where you have detailed comparisons, is that where were you getting the constraint? Was it from one of these algebraic models?
We have tried algebraic model. We have tried the SA model. They don't have to show any difference. Essentially, very good compared to each other.
Actually, could you summarize for us one more time what constraints you used for your calculations?
Okay.
And,
I think
these
it's
constraints have to change from one flow to another.
no. We just constrain this. Okay, let me go back. Thank you for asking the question. That's crucial. Here. Okay. If you look at this term for large eddy simulation is known. There essentially this term, because we want to constrain the average of your subgrid scale, the subgrid stress. Therefore, but we don't know this quantity. But this quantity essentially is given by the detached simulation. You are using the SA model or you are using algebra model. So what I say, we put this term, you solve the Reynolds equation, then put it back to here to constrain your subgrid stress. So where constrain subgrid stress? The mean quantity.
What exactly do you do to LES? What do you mean by constraint?
So essentially, after that's way.
I have UVW, so what do I do to that?
Okay. So essentially, if you know this mean quantity tau ij, because you see, I separate this tau ij to be mean and this. My mean is known now. Now I solve fluctuation, only need to solve fluctuation. I can do fluctuation solved by dynamic Stravinsky model. I got the mean from your Reynolds. Okay, either you use SA model or whatever model you're going to provide. I still solve my fluctuation part, add them together to be my real stress. So now your mean quantity stress satisfies the Reynolds. Your fluctuation controlled by dynamic Stravinsky model.
We will sit down and we will pay.
Sure, that's exactly this meeting for. Yeah, right.
Have a question?
Yeah.
Now, to ask the obvious question, the epsilon model, Sparta model, Mars model will give the wrong.
I could not hear you, sir.
The epsilon model or Sparta Mars model will give you the stresses, but the epsilon model will give you the wrong stresses, so you're the wrong normal stresses. So
That's
you're
right.
constraining it to be wrong.
That's why I did not present a K echelon. Yeah. So essentially, that for algebraic model and SA model, that's what I say. They are same. They are very consistent.
But my question is, if you constrain it,
If you, if I,
thing, does it
that's right.
still give you
If
the-
I'm going to use a wrong model, I may get the wrong results. Okay. So essentially, on the other hand, this is bad or good. It could be bad or good. Let me tell you. Why is good? Because SA model people believe good for separation. But SA model, then I can use SA model for separation.
No, but it gives you the wrong normal stresses. It will give you the right shear stress. And is it enough?
No, I do, for SA model, I do both, all of them. I do RIJ. I do RIJ. I constrain RIJ here.
Yeah, another question.
I know. When Pionelli did the so-called PES, he saw, like you pointed out, there's a very little fluctuation in the Reynolds region. It caused a problem. He put some forcing term to energize.
That's right.
ad
That's right.
hoc
That's
manner.
right. That's right.
Now you're doing exactly same ad hoc manner in the sense that when you solve the LES with the full resolution, you got the tau ij,
That's right.
which is wrong. So now you're going to replace that with the mean value of the tau ij coming from your Reynolds type model.
That's right.
I mean, putting that mean value elevate your tau ij, so it does increase your energy transfer from
That's
the
right,
Reynolds LES. But this sounds very ad hoc. Why the mean value of tau ij has to come from totally different calculation?
Let me tell you. Essentially, I'm not going to invent the wheel. Let me tell you. The wheel is, I have a Reynolds here. I have LES outside. Okay, you need a transition time to push the boundary out. Okay. Now I say, I give you mean. I give you outside LES. I don't need it. You see the point. There are people are using forcing scheme over there. Forcing scheme time correlation is not correct. You know that is a white noise. This way, giving you the time correlation is consistent because you are solving the LES. So there a little more. I don't claim you have a lot more, but seem like you see the results.
But that
consistent.
LES near the wall is wrong because you don't have the resolution to get the LES corrected. So you're using that wrong fluctuation with the correct mean. So
You are pretty much is correct. But if you are interested in certain quantities, for example, you're interested in drag, you're interested in separation, SA model we know is pretty good. Outside you need something. So what I'm trying to say, if you do the problem like this, like you want to calculate drag, you want to know separation well, you want some type of interaction. This model may provide something.
I actually want to go back to the question Srini asked you. And I think that you basically have to rely on the fact that the RANS is giving you the right answer near the wall, right mean.
That's right.
And in effect, if let's take.
That's I need this guy. They tell me the mean is correct. I even can use this measurement and put over there. In fact, I tried it. You just put the quantities over there.
Yeah,
Then,
but the problem I want to point out is that, for example, let's take a boundary layer with various pressure gradients. It's not clear that at least the current triangle's capabilities give us the right answer in these. As the pressure gradient
I'm not
changes.
going to defend that. What I'm trying to say, as long as they give me the best model of range, I'm going to put over there. Okay, I'm going to get a better result than the DS philosophy.
Maybe it's tea time now.
Thank you.
Thank you very much.